All right, in section 6.4, we're going to take our exponential function, y equals ab to the x power, and actually talk more about what that means in the way of exponential growth and exponential decay. So, what are you going to learn? You're going to use and identify exponential growth and decay functions. You're going to interpret and rewrite exponential growth and decay functions, and then you're going to solve real life problems involving exponential growth and decay. So we're going to start with exponential growth. Exponential growth occurs when a quantity increases by the same factor over equal intervals of time. Here's your core concept. Exponential growth functions. A function of the form y equals a, notice this is your b, which is now 1 plus r to the t power. A has to be bigger than 0. Has to be positive. R has to be greater than 0, because if it isn't, it's not going to be growth. So this is exponential growth. Now before we do anything else, I'm going to actually do this. Y equals a b to the x power. If b, for example, is bigger than 0, let's say that it's 2. So we have y equals, let's do 7 times 2 to the x power. And then we say it's a half. This is going to represent exponential growth. This is going to represent exponential decay. Because this number is bigger than 1, every time you multiply by 2, it goes up. But since this number is less than 1, it's going to go down, because the more you multiply by a half, the smaller the number gets. So there's one more factor, or one more thing I want to look at, and that's your study tip. Your study tip says this. Notice that the exponential growth function is of the form y equals a b to the x power. But b is replaced by 1 plus r, and x is replaced by t. So it's taking what we learned in 6.3 and applying it to real-life situations. Example 1, using an exponential growth function. The inaugural attendance of an annual music festival is 150,000. The attendance y increases by 8% each year. Write an exponential growth function that represents the attendance after t years, and then how many people will attend the festival in the 5th year. Round your answer to the nearest 1,000. Now, going back to what our core concept was, here's what we need to look at. The y value is your final amount. What you start with, or your initial amount, is a. The rate of growth is always going to be in decimal form, and t is time. Now, this entire thing, whenever you take your rate of growth and add 1, this entire thing, which is your b, remember the growth factor is going to be your b. So that's called the growth factor. So let's get rid of that and start with the problem. So we're going to start with y equals a times 1 plus r to the t power. So y equals, what's your initial amount? It's 150,000. 1 plus r, well, your rate of growth is 8%, but 8% as a decimal would be 800ths. And t is time. We leave that alone. So we add this together, you get 150,000 times 1.08 to the t power. That's A. Now B is figuring out what the attendance would be, what does it say? In the 5th year. Since the first year is represented by 0, the 5th year is going to be when t equals 4. So all you do, and I'm not going to write it down, but all you do is take this and just plug it in. 1.08 to the 4th power times 150,000 gives us approximately 204,073 people. But the answer asks us to round to the nearest 1,000. So about or approximately 204,000 people will attend. Now, exponential decay is when a quantity decreases by the same factor over equal intervals of time. Everything is exactly the same except your R value. Your R value has to be between 0 and 1. So which means when you take 1 minus R, notice it's minus now, remember growth, you add it on. Decay, you subtract it. So we're going to subtract, and then that's going to give us something called our decay factor. So now, exponential growth. If we have exponential growth, the value inside the parenthesis, which is the growth factor, has to be greater than 1. If it's exponential decay, the value inside the parenthesis is going to be less than 1. So example number 2, we're going to identify if it's exponential growth or exponential decay. So, pretty easy. We're going to start with our first solution. We can see that each time this is increasing by 1. X is increasing by 1. What are you doing to go from 270 to 90 to 30 to 10? You're dividing by 3, but we always want to use the growth factor or a factor of multiplication. So dividing by 3 is the same as multiplying by a third. So what does that mean? That means that as x increases by 1, y is multiplied by a third. So the table does represent an exponential decay function. Why is it decay? Because y is being multiplied by a third, which means it gets smaller. It's decay, it goes down. In the second example, x increases by 1, y increases by being multiplied by 2. So as x increases by 1, y is multiplied by 2. So the table represents an exponential growth. Pretty easy. So in example 3, we're going to interpret and rewrite the exponential functions. So we're going to determine whether each function represents exponential growth or decay and identify the percent rate of change. Now I'm hoping this becomes really easy for you. This should require no work. If we look inside and this number is bigger than 1, remember, growth is when you add something to 1. Decay is when you subtract something from 1. So if the number is bigger than 1, it's growth. If it's less than 1, it's decay. So we know right off the bat, this is growth. Now, what did you add to 1 to get 1.07? It's basically saying this, 1 plus r equals 1.07. Well, obviously you added 0.07, which means the growth or the rate, which is what we need to find, the rate, the percent, is not a decimal, it'd be 7%. So growth and 7%. This should be very easy. This is decay because it goes down. And by what has it been subtracted to get 0.98 from 1? You subtracted 0.02, which, as a percent, is a 2% decay. So the growth rate in A is 7%. The decay rate, or the rate of decay, is 2% in B. Rewriting exponential functions in example 4. Rewrite each function to determine whether it represents exponential growth or exponential decay. You'll notice that both of these are not, they don't have t on them. So that's really, really important that we understand that there's no t. So what you have to do is use the properties of exponents. So what we're going to do is rewrite it. So A, we're going to rewrite it as 100 times 0.96 to the 1/4 to the t. Notice I took the t to the 4th, or I'm sorry, I took the t divided by 4. I took the 1/4 out. Remember, power to power I multiplied. So I just divided it out, and I got 0.96 to the 1/4 power. Well, if you take the 4th root, which is what the 1/4 power is, the 4th root of 0.96, you would get approximately 0.99 to the t. So what is that? That represents decay. In B, where you get f of t equals 1.1 to the t minus 3. So now we have to do the quotient of powers. Remember, we're subtracting. And when you have the same base, we subtract the powers. So this is what we did. If you actually subtracted these bases, you'd subtract t minus 3. So now, we simplify this. evaluate the power, f of t is approximately equal to 0.75 times 1.1 to the t power. And how do we get that? We take 1.1, this is going to be to the negative 3, because remember it's going to be this. We have to move it to the top. And 1.1 to the negative third power gives you 0.75. So this, because it's 1.1, this represents growth. So now we're going to solve real-life problems, because this is going to be fun. Exponential growth functions are used in real-life situations involving compound interest. Although interest earned is expressed as an annual rate, the interest is usually compounded more frequently than once per year. So the formula, here it is, must be modified for compound interest problems. Here's your formula. Compound interest is the interest earned on the principal and on previously earned interest. What that means is that if you have a credit card and you do not pay your bill monthly, you are not only paying the interest on what you bought, but also the interest on the interest from the month before. The balance, which is what you need to pay, is your Y, of an account earning compound interest. The P represents what you started with, or what you borrowed. The R represents the annual interest rate written as a decimal. T is time in years. And N is the number of times interest is compounded per year. This is much easier than it looks. Example number 5, we're going to write a function. You deposit $100 into a savings account that earns 6% annual interest compounded monthly. Write a function that represents the balance after t years. All we have to do is plug stuff in. The principal is what you started with. You started with $100. 1 plus R. R is the rate. The rate's 6%. But we have to write it as a decimal. Divided by n, which is the number of times interest is compounded. Here we're compounding monthly. So monthly would mean 12 times in a year. And then n times t is our exponent. Well, t we leave alone because we don't know how many years. But n we already know is 12. So our equation is y equals 100 times 1.005 to the power of 12t. And that's your answer. Pretty easy. Example 6, let's do a real-life problem. The table, right here, shows the balance of a money market account over time. Write a function that represents the balance after t years. So A, let's start this problem. Y equals P. P is what our initial amount is, which is $100. Now, since we're talking about growth, since this is going up, we're going to use 1 plus R. 1 plus R. So what is the percent? Well, this is where we have to use common sense. If we look just in the first year, 100, it goes up to 110. That means it went up $10. That's a 10% increase. So that's how you find the percent of increase. So 10% will be plus 0.10 to the t power. So that would give me y equals 100 times 1.1 to the t power. That's it. Now it says graph the function. So if I graph it, it's right here. So graph the function from part A, which is right here represented in blue, and from example 5. Well, if we look at example 5, that was 100 times 1.005, 12t. And that's right here. Compare the account balances. Now, it's completely up to you how you want to compare it. However, this would be a good thing to write down. I would say that the money market earns 10% each year, and the savings account only earns 6% each year. So the balance of the money market increases faster. So you would say you would make more money in the money market because it goes up 10% while the other savings account earns 6% interest each year. All right, our last problem. The value of a car is $21,500. It loses 12% of its value every year. Therefore, it's exponential what? It's exponential decay. Write a function that represents the value of y in dollars of the car after t years. So let's start there. A. Y equals, now remember, it's going to be y equals A times 1 minus r to the t power. What's the initial amount of car? $21,500. It loses 12%. So that means it's going to be y equals 21,500 times 0.88 to the t power. Really easy to write that. Now part B says find the approximate monthly percent decrease in value. So this gets a little tricky. I'm going to rewrite it. Since I'm talking about monthly, I'm going to take the time, which is right here, and rewrite it as 12t over 12, because that's the same as t. We're talking about monthly. And then I'm going to separate it. I'm going to take the 1/12 and use the power of exponents, or the rules of powers of exponents, and bring it inside. Now, if I simplify this, 21,500 times approximately 0.989 to the 12t power. The monthly rate of decay is about what? Well, we know 1 minus something gives you 0.989. So it's approximately a 1.1% decrease in value monthly. C says use the graph. So we want to use the graph to estimate the value of the car of 6 years. So I graph this, which if it says use a graph, use a graphing calculator. Punch into a graphing calculator and see what it says. So after 6 years, what is the approximate cost? It's going to be approximately a value of $10,000. If you double check your math, this is important. If you actually wanted to plug it in, which is actually a better deal anyway, is to take your original equation and for years, plug in 6. So after 6 years, figure out what it would cost. And if you did plug that in, you would get, actually you get about $9,985, which is approximately $10,000. I've already explained this, but I'm going to write it down. And actually, if you want to write it down, please do so. Make sure you understand this. For the exponential growth, the value inside the parentheses is greater than 1. For exponential decay, the value inside the parentheses is less than 1.